Hello, in this video we're going to take a sort of step back, see where we are on everything, and look again at matter, energy, force and work. And this is a step back because if you think of the first video that we had when we were talking about what physics actually is, and these are our main topics. These are all of the key ideas in physics here. So we've got matter and energy, where everything in the universe is made of matter and energy. We've got force, which is moving matter and energy around. Then we've got this idea of work, which we haven't really discussed yet, but work is the relationship between force and energy. The other topic that we've covered in physics that we were talking about back at the beginning is motion, and we've been looking at motion quite a lot already. So out of these key ideas, we've already been discussing matter and force and motion. So now I want to bring in energy and work. So we've got a nice overview of the whole subject, and we can see how all of these key ideas interact. So let's make our first steps in getting a definition of what energy actually is. And we know from experience with trying to define what matter is that getting a definition isn't always the easiest thing. And we're going to have the same problem here with energy. But as usual, we don't want to let that put us off. Let's just build up our understanding of energy as we go and then see where we end up. So first of all, we're going to say a couple of things about energy. Let's keep it simple. First of all, energy is a property, it's not a thing. So what I mean by that is it's not some thing where you can just go and pick it up. You can say, oh, here's some energy. Let's look at this energy. It's not like that. It's not an actual physical thing. It's an abstract property of an object or a system of objects. So that does make things more difficult in terms of understanding what energy is. But it's the fact of how energy works. It's an abstract property. It's not something we can actually see, but it is something that we can quantify, and we can quantify it mathematically. And a lot of the physics that we do is based around working out how we can assign an actual value to the amount of energy that's located in a particular place. So that's a lot of the work that we're going to be doing in physics around energy. In terms of saying what energy actually is, the best thing I think we can say at the moment, because it fits with our everyday use of the word energy as well, that energy is the capacity to do things. And like I say, this is how we describe energy on a day-to-day basis anyway. If you feel as though you're full of energy, then you can get a lot of stuff done. If you've got a battery which is fully charged and is full of energy, then it can power things. So energy has got something to do with this capacity to make things happen. That doesn't mean to say that it's going to necessarily cause those things to happen. I mean, you could be as full of energy as you want, but that doesn't mean to say you're necessarily going to do anything. There needs to be some kind of impetus for things to happen, and this is where forces come in. But without energy, you're not going to be able to do anything. The battery isn't going to be able to power anything. We need energy for things to be able to happen. So that's where we're going to start with our definition of energy, and we'll just keep on building that as we go through different ways of quantifying energy and how it relates to things such as force and work. So setting aside the problems of defining exactly what energy is, let's look at how we're actually going to use energy, because that's what we're more interested in at the moment. We want to be able to use the idea of energy so that we can describe the universe. That is our primary objective as physicists. And the key to all of this is the work energy principle. So we're bringing in this idea of work or work done, the same thing depending on what you want to call it, and then the idea of energy. So we're linking these two ideas together, work done and energy. And this also brings in the idea of force. So we've been talking about forces a lot already, and we know from real life, if you think of, we've got some object sitting on the floor and we want to pick that up, we exert a force on it, we lift it up, we're having to use energy in order to raise this object up into the air. So we're exerting a force, which is something to do with using energy, whatever using energy means, and we'll get onto that in a moment. And this process is what we're going to call work. So work done is the application of a force through a distance. So if we've got some force F and we move it through a distance D, then the work that we do on this, our work done, is equal to the force that we've exerted multiplied by the distance. Now it's simpler in this case because we've moved the force just in one, straight direction. The force is applied in the direction we're moving it. This won't necessarily always be the case. Say we had our object was sitting on a sloping surface and we were pushing it in that direction, so pushing it in a horizontal direction, and then the object was then moving up the slope. So we're not pushing it, the force isn't being applied in the direction of motion. So in this particular case, the work done is the component of the force that acts in the direction of motion. So if the slope is on an angle of theta to the horizontal, then the component of the force is going to be F cos theta. So our work done is going to be F times D cos theta. So that's a way of quantifying work done in terms of force, but we can now link this in with energy because we're also saying that that is equal to an energy transfer. So it's an energy transfer from one place to another. So going back to our definition, as sort of simple as it is at the moment and a little vague, our definition of energy. So energy is some property of an object or a system of objects. This is what we were saying before. It's something that we can quantify mathematically. So energy is either sitting in some object or some system of objects, however many that may be. It might be one object on its own, or we've got a group of objects. And every time we perform work, we're moving energy around. It might be from one object to another object, or from a system of objects to a single object, or from a single object to a system of objects. So in some way, energy is being moved from one location to another. All right, so what might be happening here in these cases, if we've lifted up this object, so we've used energy picking it up, so energy has moved from us, say our muscles, into the object in some way, or in this case a system of objects, because we've lifted the object up in the air, which has increased the separation between the object and the earth, and it's increased what we would call the potential energy, and I'll get onto this in a moment, of the system of the object and the earth. So we've transferred energy from our muscles to the system of the thing that we've lifted up and the earth, that gravitational system. So this work energy principle, which is one of the foundational principles in physics, and we're going to be using this loads, particularly in classical mechanics, but also in some of the other topics. It's so powerful because it gives us that link between force, work, and energy transfer. And because we can calculate using these equations here, we can actually calculate the work done. That means we can quantify energy transfers. So it gives us more mathematical power of actually being able to describe these systems and what's going on. We can quantify all of these things because we can measure forces, we can measure distances and these angles, so we can measure this work done. We'll also have ways of calculating energy, which means we can work back in the opposite direction. So if we've got a particular energy transfer, this must be the force that's applied, or this must be the distance that force is acting through. So really powerful way of pulling together three of the the key ideas here in physics of energy, force, and work done. Now, I've mentioned a couple of times already that energy can either exist in a single object or in a system of objects. So let's quickly unpick that a bit. If we got a single object, and this is the easier one to deal with, we've got kinetic energy, and that's based on the motion of the object. So as I'm sure you're all familiar with, the kinetic energy of an object is 1/2 times the mass times the velocity squared. You'll note that this is a relative value because the velocity is going to depend upon our frame of reference, something that we've been talking about quite a bit already. So there's no absolute value here of kinetic energy. It's going to depend upon how we've set up our reference frame, but that's fine because usually we're looking at changes in energy before and after certain events. But that is our energy associated with a single object. It's just based upon the motion of that object. Now, potential energy is when we get into systems of objects. So we've got one or more objects which are situated in some configuration. And then the potential energy is a property of this whole system of objects and how they are located relative to each other. So as an example, you might have a gravitational system. This might be the Earth and a couple of satellites orbiting around the Earth. So the gravitational potential energy is based upon the relative locations of these objects in the system and then the masses of the system, of the objects in the system. So potential energy is position based. Kinetic energy, it doesn't matter where the object is relative to other things, it's just based on the motion of that individual object, whereas potential energy is based on relative position. And there's loads of different potential energies, and we'll be going through lots of different ways of calculating them. We've already started looking at gravitational potential energy. We're going to have later on, we'll be looking at electromagnetic fields and say electrostatic potential energy. We'll be looking at stretched springs and rubber bands and things like that and getting elastic potential energy. So there's lots of different ways that potential energy can exist within a system of objects, and part of our job as physicists is to be able to quantify each one of these, but you have to do it in a different way each time, whereas for kinetic energy we've just got one nice little formula that we can use time and time again. We will run into some complications in later topics with this, particularly if we're looking at something like light and electromagnetic radiation, where this kinetic energy, potential energy split isn't quite as clear cut. But we don't have to worry about that at the moment when we're just starting out looking at energy and we're in the realms of classical mechanics as we are at the moment. So this is fine for what we need at the moment.